So we can represent compounds using chemical formulas. The chemical formula is going to show us the different elements that are present in that compound and also the relative number of atoms or ions of each of those elements. And this is a shorthand way of describing compounds that people decided to agree on. Sometimes that happens. So we use a subscript following the element symbol to tell how many atoms of that element there are. So here's a couple of examples. So water is H2O. The subscript 2 is coming after the H. So that tells me there are 2 hydrogens. Oxygen doesn't have a subscript of 1. But if there were no oxygens, we wouldn't write the symbol, right? It would just be H2. The fact that we wrote the symbol means there's 1. Again, chemists avoid writing the number 1 whenever possible, it appears. So H2O, this is going to have 2 hydrogens and 1 oxygen. Sodium chloride can be represented this way, NaCl. How many sodiums? 1. And how many chlorines? 1. Here's another one, carbon tetrachloride, CCl4. So 1 carbon and 4 chlorines. Now this can be a little bit confusing because it looks like there's C, C, and maybe that's an I, right? C and C would be carbon said twice, and we would never do that. If it was 2 carbons, we'd say C2. So this is C and that's Cl. I chose this font particularly because the lowercase l and capital I and the number 1 actually look different in this font. Some fonts they don't. We can break chemical formulas down into 3 different types: empirical, molecular, and structural. Molecular formula is what we're going to deal with most of the time. The empirical formula just gives us the relative number of atoms. It doesn't tell us how many are in a molecule. It just gives us the ratio, basically. So the example here would be hydrogen peroxide. So hydrogen peroxide has a molecular formula of H2O2. That tells us that in one molecule there are 2 hydrogen atoms and 2 oxygen atoms. Its empirical formula, though, is HO. Empirical means from experiment. The empirical formula can be determined using often some simple experiments. In experiment 3, we're going to determine the empirical formula of zinc iodide. It doesn't require a lot of technology or anything, fairly simple. In order to find the molecular formula, we need more information. So this is basically what you can find from experiment. It's the lowest ratio. The molecular formula is going to give us the actual number of atoms. So we can take the molecular formula and figure out what the empirical formula would be. So C4H8, this has 4 carbons and 8 hydrogens, and we can think of that as a fraction that needs to be reduced. 4/8. And we're going to factor things out of it. Each of those has a factor of 4, and so this is also equal to 1/2. So 1 carbon and 2 hydrogens, that's the lowest ratio. B2H6, 2 to 6, that can be reduced to 1 to 3. So this is the empirical formula. This is the lowest ratio, but this is the actual number of atoms in a molecule. For CCl4, we've got a ratio of 1 to 4, and that cannot be reduced anymore, and so the empirical formula and the molecular formula for this one are the same. Any questions about that? Most of the time we use molecular formulas, but sometimes we'll use empirical formulas and we need to know what they are. Structural formulas are going to give us a little more information. They're going to tell us how the atoms are combined. Yeah, question?
I'm still trying to find a difference between empirical and molecular.
Okay, difference between empirical and molecular. So the molecular formula actually tells us what's in a molecule. So this is a molecular formula. One molecule of this has 4 carbons and 8 hydrogens. The empirical formula just gives me the ratio of carbon to hydrogen atoms. And so, in math class, you probably were taught that you shouldn't have a fraction that's like 4/8. You should reduce the fraction, right? That's the same as 1/2. So the empirical formula is always going to be the simplest ratio or the lowest, the reduced fraction. Does that make sense?
The empirical is reduced.
The empirical is reduced. Yeah. The empirical is reduced. So I think molecular formula is the easier one to identify because it tells us what's in a molecule. It's the formula of a molecule. Okay, that molecule has these pieces in it. The empirical is where you take that molecular formula, and if you can reduce the ratio, you do so. Does that help? The structural formula then is just going to show us how the atoms are combined, and it may indicate single bond, double bond, or triple bond, and it does this with lines.
Are we ever going to be given the empirical formula and asked to give the molecular formula?
Yes. Yes. There will be times where we give you the empirical formula and we ask you to tell us what the molecular formula is. You need some more information to do that, but you'll be provided with enough information to figure it out. It's a great question. There's not really an example here, but like for B2H6, the empirical formula the structural formula might look something like this. From this molecular formula, you can't necessarily predict how the atoms are bonded together. Are all the hydrogens in a line and then the borons at the end? Or how does this work? So the structural formula tells us, okay, the borons are bonded to each other, and then each of them has 3 hydrogens bonded to them. And so it gives us more information. Which formula we use depends on how much we know about the compound and how much we want to share about the compound. The structural formula gives more information, but it's also more awkward to enter into a computer, right? To type it out is very difficult. You just really need some drawing software. An empirical formula communicates the least information. The molecular formula is kind of a compromise. It actually tells us what's in a molecule, but doesn't tell us how it's combined. But it's easier to type. So more information is more difficult to type. Yes?
With the structural, molecular formula, are we going to need to balance those? Do we get further into it, or balance them now? Is that necessary?
Well, so when we talk about formulas for ionic compounds, those can be predicted based on the charges of the ions. Molecular formulas for molecular compounds are not necessarily predictable, but we will learn how to write them from the name of the compound or write the name from the formula.
So we won't need to worry about balancing it out.
We'll be balancing equations,
Okay.
but not formulas.
Got it.
Mhm. So this is a little exercise to find the empirical formula given the molecular formula. So the molecular formula is C5H12, and we have to write the empirical formula. Well, that's a ratio of 5 to 12. Can that be reduced? No. So the empirical formula is the same, it's just C5H12. Hg2Cl2, the ratio is 2 to 2. Can that be reduced? Yeah, so what would it be? Just HgCl. It's a 1-to-1 ratio. There could be more than 2 elements. C2H4O2. So that's 2 to 4 to 2. And can we factor something out of all of those numbers? Yeah, we can factor out a 2. So 2CH2O gives us the same ratio, reduced. We can also have molecular models. And you can get molecular model kits, and those can be really helpful if you like to get your hands on things. So that's what's called a ball and stick model. The balls are color coded. This is the typical system of color coding, so that we can remember what's what. And so if I look at this guy, it's got 2 black carbon atoms and 2 white hydrogen atoms and 2 green chlorines. The atoms get represented as balls, and the chemical bonds are sticks, and how they connect together gives us an idea of the molecule's shape. You do not need to memorize these colors. We can also draw or create space-filling models. So here we have 4 different kinds of formulas models presented. So here's a molecular formula. The structural formula shows us that all the hydrogens are bonded with single bonds to the carbon atom in the center. The ball and stick model gives us more of an idea of the shape of a molecule. This looks like it might be flat, right? 2-dimensional. But it's actually got this 3-dimensional shape. The space-filling model is closer to the actual shape of the molecule, because when atoms bond to each other, they kind of get pulled into each other and they overlap, and that's part of the bond. And so they'd really look more like this. They don't look like Tinker Toys. Yeah. But we should be able to look at any of these and understand what they represent. Here's an example, 4 different compounds and 5 different ways of representing them. So here's the empirical formula, the lowest ratio. Let's just look at glucose. The empirical formula, CH2O. The molecular formula tells us how many atoms of carbon, hydrogen, and oxygen are in a single molecule. There's 6 carbons, 12 hydrogens, and 6 oxygens. But that doesn't tell us how they're put together. This is actually the molecular formula of a number of different sugars. They all have the same molecular formula, but how they're connected is different. And so here's the structural formula for glucose. And we see there's OHs over here and over there. And then we can represent that with a ball and stick model, or a space-filling model. One of the hard things about the space-filling model is if you don't have the actual model, you can't see what's on the other side, right? And so you can't see all the atoms. Because these are separated, the little balls are separated and connected with sticks, it's easier to see what's there.